So, hello everybody. It's a big pleasure for me to be here, and I would like to thank Dr. Vangelis Papoutis, so the organizer, Professor Zanakoglu, and you that invited me to this presentation. So, just as a start, the other acknowledgements go to the people that every day work with me, the development of the application that I'm going to present. It's Professor Dr. Federico Ghioldi, assistant professor that is working with me, Jerome Lee, Sasha Ital, Filippo Giussani, Ivan Spisso, and Joel Guerrero, and all the master students that are working at the Department of Aerospace and Technology under my supervision that contributed to the results that I'm showing. What are we do and who we are? We are from the Department of Aerospace and Technology, Politecnico di Milano. We work on propulsion CFD and CFD methods as well. We work to the development of library development that can be sticked to OpenFOAM and to applications that are going to the official release of OpenFOAM. And the aim of our work is clearly to push towards more and more realistic simulations of very complex multiphysics phenomena. So just a start, I will be very brief because I know that many of you are know very well this story, but if you look at the CFD history through the years, you can see that the success of CFD through the years has been strongly linked to the evolution of computer systems. If you look at the history of the CFD in the 70s, between the 60s and the 70s, the first CFD applications were coming up. In the 80s, the first CFD service industry started up, while we had to wait up to the 90s and the 2000 to wait for the CFD industry could expand significantly into the market. If you look at this time frame, you should immediately understand that the evolution of HPC systems and the increase of computational power available for everybody was the key aspect that allowed to CFD to penetrate deeply into the industry, into the for industrial applications. So in this context, we talk about OpenFOAM. This is an OpenFOAM class, so you probably have seen many features of this code. Why at Politecnico di Milano, the Department of Aerospace, we selected OpenFOAM as a big platform over 20 years ago. And this was due to several reasons. First, because it is a ready-to-use CFD code that includes application and state-of-the-art models for CFD that are available already in the code, and includes all the state-of-the-art and let's say, the newest features that allows the application of this code to very complex industrial problems. On the other hand, the code is open source, object-oriented, and it has no license cost, allowing everybody to put its hands on it, modify it as he wants, and favor to link to a large network of developers and users using the same kind of platform. So what is OpenFOAM history? OpenFOAM is a code that dates back in the 90s, and in 2004 it became open source. And from 2004 to 2024, many things changed, and it evolved very much up to become up until now. And today it's a very well-established CFD code that is very known, and it has a very large user database. So going back to the topic of this presentation. We basically want to see how CFD and HPC are linked to each other and how HPC can be applied to CFD to simulate challenging problems. Okay, today the most challenging problems among the wide number of challenging problems that we have in CFD, basically the a big effort is done to simulate multi-scale and multi-physics problems. What are multi-scales? Multi-scale problems involve different spatial and temporal scales, meaning that interact each other to obtain the overall final solution. A typical example of multi-scale problem is the turbulence, where you have small scales and large scale that interact very much together. These has a significant impact on the simulation of your on the time duration of your simulation, because if you want to simulate small scales, usually you are forced to increase the mesh resolution and to clearly decrease the time step advancement. I think that many of you know the CFL criterion, Curran-Frederick-Lewis. Basically, as long as you decrease the mesh, so as long as you increase the mesh resolution, so that cells become smaller, the time step becomes much smaller. And so you need to reach the final time step of your simulation. You have to iterate to resolve a larger number of time integrations that make your simulation much longer. The second kind of simulation that is very computationally intensive is the so-called the multiphysics problem. What is a multiphysics problem? You can see it hopefully well in this example here. You have the CFD solution, which is typically the flow transport, so the solution of mass, momentum, and energy, which is linked to a secondary problem called the multiphysics problem, that is whose solution is driven by the solution of a different set of equations. A typical example is what we have in reactive flow simulations, where you have the flow transport that is coupled to the solution of the ODA chemistry mechanism, of the finite rate mechanism for chemistry. In this case, you have two different problems that have two very different time scales. Usually the time scale of the chemistry problem, the finite rate chemistry, is much smaller than the time scale of the flow transport. And this forces you to limit your time step evolution significantly and also makes your problem very computationally intensive, because you have two sets of equations to solve at the same time. So up to 10 to 20 years ago, these problems were considered extremely challenging because the computational power was not enough to solve these problems on an industrial scale. Today, thanks to the HPC, we can see that these problems are becoming more and more feasible to be done on the daily use. So what we are looking at is that the structure of a CFD solver. Here you can see how generally a multiphysics CFD solver works. We have the flow transport, so the solution of the partial differential equations of momentum, energy, species, transport, and mass, that is done on a first block, which is called the CFD block. This solution is linked through source terms to the multiphysics problem, so to the logarithm physics, that most of the time is solved by ordinary differential equations. There is a large number of examples of multiphysics problems. I will show you only a few of them, related mostly to what I'm working on. So as another aspect that we cannot neglect when we look at the link between CFD and HPC, is the so-called hardware architecture. As you have seen recently, the evolution of the hardware has been massive in the last 5 to 6 years. And we are going to exascale, and now we are in the exascale time. So we have machines that are able to perform a very large number of flops, but the hardware architectures are changing significantly. So while in the past, from 2000 to 2020, we basically had an evolution of the hardware that the hardware is increasing its potential and its number of operations, while the architecture was kept the same, basically, or anyway, was not significantly different. Today, we have the introduction of the GPUs into the hardware in the HPC systems. The GPUs are have a large power, have a very good performs a very large number of computations per time, meaning that if we are able to exploit the potential of the GPUs, we can actually increase the number of operations, and we can switch to larger and larger problems to solve. On the other hand, GPUs hardware and GPUs architecture is very different from GPUs, so it is required a co-design of the software to fit the requirements of the graphical processing units. In other words, the CFD code developments must adapt to the hardware where it's going to run. We have two examples of clusters here that we are using for our computations. And it's the Da Vinci cluster by Leonardo Aviation and the cluster from Argonne National Labs. Both of the clusters employ a CPU and hybrid architecture featuring where there are several nodes, featuring a number of cores that goes from 40 to 64 for each node. And they have 4 GPUs for each node. So our goal is to use the GPUs to speed up our computations. What are examples of very large computationally intensive problems? Well, a typical example is the external aerodynamics. You have a car or you have a geometry. You want to solve the flow around the body. Usually these are steady state simulations that have a very large, most of the cases, not always, there are also unsteady LES simulations that are employed, but by the way, these are problems that have very large number of cells where the flow transport is very computationally demanding. Typical simulations like this can run traditionally on 1000 cores, but our intention is to reduce the number of CPU used and to port most of the calculations onto the GPUs. Another example of computationally intensive simulation that you can find is the external aerodynamics of the wings into the large vessels. This is the example of the boat that was taking the Ariane 5 to the station, to the launch system. Basically, we have like a 500 million cell mesh. We have 4 wings that are 4 double wings that can be oriented, and they must be oriented to optimize the aerodynamic of the flow while the boat is moving. This kind of system is called the wind assisted propulsion system because this kind of large vessel have a propulsion system that is based on an engine, but we have like the wings here that are helping the boat to move, and they are working to decrease the specific consumption of such a boat. The goal of the simulation here is the typical goal to optimize the aerodynamics, but clearly the other aspect that is very crucial for us is that we want to define the optimal shape of these wings with a turnaround time that is 1 day. So in other words, if we run these simulations onto CPUs, we are forced to wait pretty long for a simulation. But if we are able to accelerate our simulation, we will be able to reduce our turnaround time. So this is what I will show later. Other examples of problems that are pretty computationally intensive, these are optimization problems. I will not go further here because we have the very big experts like Vagelis and Professor Giannakoglu about the topic. But I will go to multiphysics problem that is mostly related to combustion and aerospace. So when we talk about multiphysics, I already explained what we are talking about. So an example of multiphysics problem is the simulation of the spray over a large vessel. So what we can do here, we have an aeronautical engine. We have a liquid spray that is injected into the engine, and this spray atomizes. So when we have a CFD simulation, we have a multiphysics solver because we have the flow transport that is solved in the continuum phase by the partial differential equations. And then we have like Lagrange, a lot of Lagrangian droplets that are evolving into the domain and are interacting with the walls. What is the problem here to solve? When we inject the liquid into combustion chamber, basically the liquid hits the walls, and generates a wall films over that. If the wall film generates into the combustion chamber, we have two kinds of problems. The first one is that the liquid film does not evaporate and increase the number of pollutants that are generated by after the combustion. The second problem is that the efficiency of the combustion decreases because clearly we don't burn fuel, but we use it to generate a wall film onto the surface. So we have to do two kinds of studies. First, we have to minimize the number of parcels that are going to the walls. So we have to orient the spray properly. And then we have to design our injector to favor a bigger atomization of the injector to favor its mixing within the combustion chamber. These kind of simulations are very computationally intensive and they can last even weeks. The reason is because we have two sets of equations to solve. We have the carrier fluid that is in gaseous phase here, that is solved by the CFD solver, and we have the Lagrangian particles that are solved by ordinary differential equations that are tracked onto the domain that we are going to simulate. Another example of multiphysics problem is the volume of fluid simulation of the liquid injection. Here we have an aeronautical injector. We have the liquid that is going out of the injector. As you can see here, the aeronautical injector has like a liquid that is swirled into its nozzle. This swirling generates an atomization. When the liquid gets out, it's partially atomized, and the shear between the carrier fluid and the liquid generates a Kelvin-Taylor instability that favors the atomization of this liquid. Our goal, what is the goal of the injector design? Well, the main goal is that we want that as long as the liquid gets out of this nozzle, we want that it is almost completely in the gaseous phase. In this way, it will be able to mix with the surrounding air, and it will burn very fastly, giving us a strong propulsion efficiency. What is, as if you see here, this distance that here seems so large, is less than 1 millimeter. And what we want is that in less than 1 millimeter, a huge amount of liquid that is injected at over 100 bar atomizes completely. So the two things that we want to study is that the amount of cavitation that generates from the interaction between the liquid and the air, so the turbulent swirling that is happening here. And the second thing is we want to study how much shear we have between the air and the liquid in order to favor the atomization of this liquid jet. This kind of since we are the kind of scales we are talking about here are less than 10 microns for this hole that you can see here. This channel is less than 10 micron. And we are talking about simulations here that are of the order of 100, 120 million cells. But we have to simulate an unsteady flow phenomenon, meaning that we have to simulate a very large number of seconds, or, well, let's say almost a second of physical time, in order to get a solution that is like this. What is the challenge here? Running 1 second of computational time on over 100 million cells with a cell size that is smaller than a micron and the velocity, flow velocity that is on the 100 of 100 meter per second means that these simulations were running in 3 months on 1000 core without stopping before producing the results that you can see here. So what is the goal here? On one hand, you need an HPC system, otherwise you are not able to solve this problem with such a resolution. And this was solved at the Argonne National Lab for 3 months, no stop, 1000 cores. You have a large space of disk that is required in order to employ such kind of simulations, because the hard disk, the storage becomes a significant problem, because anytime you dump your data on the disk, you actually fill it very soon if you are not smart at doing post-processing. And the third thing is that you cannot make mistakes, because if you make a mistake, you actually burn out millions of core hours that really have a cost. So even these kind of simulations that are very largely intensive, this are actually need to have an acceleration, because a 3-month turnaround time to run a simulation that today can become 1 month, because the time I was running the simulations was 6 to 7 years ago, and actually now they are faster, but still 1 month is required. We want to accelerate this time. So what are other examples of simulations that you can run by HPC? This is the combustion instability and mixing. So here you have this is what happens into a burner. The base physics is the same that happens into a burner of an aeronautical engine. You basically have an inlet jet that is swirled and exits out of the nozzle. And then you have a surrounding flow that has a certain velocity that comes from in crossflow. The mixing, the way this mixing happens nearby the inlet jet, determines how the oxidizer and the oxidant mix up together and how the combustion will evolve. If you can see here, you have the experimental visualization here, and you have the CFD simulation here that is done on a mesh that is 30 million cells after a time of 10 seconds. Be careful, as I was mentioning before, having 30 million cells in an unsteady simulation is still a decent, good challenge, because the duration of the simulation here is not given by the million of cells only, but also by the time, the integration, the time marching that is pretty limited. So the overall duration of the simulation is very large. Another example of intensive CFD simulations is the turbulence mixing between the jet and the fluid into a combustion chamber. Here you have this is an experimental test bench employed in Imperial College that has been studied by the ETH Zurich, and it has simulated by us from LES. And it is about the study of a jet flow that is entering into a valve seat and is mixing into a combustion chamber. As you can see on this geometry, if we look at the cross plane that is passing cross mid-plane of this section, we have the experimental, here we have the experimental behavior, the experimental path lines of the jet flow, and here we have the DNS and the LES simulation of the same experiment. We were using these kind of simulations to compare clearly the quality of the LES simulations to simulate such a problem, and to study how the vortex between a jet that is entering and the surrounding fluid interacts to favor the mixing during the combustion phase. Just to give you a perspective from the HPC point of view, the LES simulations last over almost a month onto 300 cores, while the DNS simulations was run by NEC 5000 on 1000 cores and 100 million cells for 3 or 4 months. So we are talking still about a very large number of cores. Okay, what is the problem today? Today, we have graphical processing units, GPUs. GPUs are the capability to produce a very large number of operations onto if they are compared by CPUs. And the second aspect, the second important non-negligible aspect that GPUs have is that they are more efficient in terms of power consumptions. Meaning that if we think in terms of computational power, with the same amount of power used, electrical power used, we can employ more operations. Or conversely, if we think in terms of operation per time of our computation, we can decrease the energy consumption. So in both cases, the use of GPU may be favorable. Also, what is it is interesting, the GPUs, because if we look at how by a survey that has been employed by the manufacturer, if we look at how the CFD simulations are employed into the market, we see that a large number of simulations is employed by in a range between 9 to 256 processor cores, meaning that the large amount of simulations are run in that size where a couple of that can be easily solved by a couple of GPUs. I'm not saying that the GPUs is the solution to any problem. We are very far from there. But what I'm saying here is that most of the people that are using CFD are running in a segment of processor range where the use of GPUs might be significantly favorable. So if we look at the GPU, if you look at the CFD solver, our question is, how can we accelerate it? So if you look at the multiphysics solver that we have in this slide, we actually have the CFD solver that employs in multiphysics, as I was mentioning, two different operations. On one hand, it solves the flow transport, and this is a partial differential equation problem where we solve momentum, energy, and species. On the other hand, we have the multiphysics problem, so we are solving ordinary differential equations. So these two problems can be definitely split thanks to the operator splitting technique, which is a very common method to solve multiphysics problems in finite volume CFD. And we can try to optimize and accelerate these two blocks quite independently. So if we look at the easiest part to accelerate is the local physics. So is the solution of the ordinary differential equations. Why I'm saying that? Because as I was mentioning before, as we were when we were talking about accelerators, I was mentioning that the hardware the GPU hardware is very different from the CPU. If we look at GPU, we will find a very large number of cores that are slow, but they are very many. They are and they communicate among each other very slowly, meaning that if we have large problems that are characterized by tasks that can be solved independently, the GPUs will work fantastically, because if any GPU core can solve independently a problem without talking to each other, that will significantly accelerate our problem if we compare that to the CPU. So the chemistry is a very good example, because if we look at the typical combustion problem, we will see that we have a finite volume mesh where we have to solve combustion. But if we look at the combustion problem in a deeper way, we will see that the combustion problem is a multiphysics problem made of two parts. A flow transport part that can be solved on the CPU, and the chemistry, the finite rate chemistry, that is a problem that can be solved on the GPU. Why? Because if we look at the solution of the finite rate chemistry, in a CFD code, each cell is treated as an independent batch reactor where we need to solve an ODE system. So if we provide any single GPU core a single batch reactor finite rate mechanism to solve, we can vectorize the solution of the computational chemistry, and we can achieve a significant acceleration, because in multiphysics problem, most of the time, the solution of the CFD is slowed down by the solution of the ODE, because the ODE here is a stiff mechanism, is a stiff problem to solve, that requires very small time steps to be solved, and limits the evolution in time, the time marching evolution of the flow transport. So if we do this, Well, we can, first of all, we can, the first test we have to do is, okay, let's solve our chemistry onto the GPU. Let's check the solutions are exactly the same on the CPU, and that is done. Then let's apply our simulation on the simulation of a scramjet engine. So on an aeronautical engine for which the experimental data are available. So if we employ an hybrid simulation on CPU and GPUs, meaning that we solve the flow transport onto the CPUs, while the computational chemistry is demanded onto the GPUs, we can achieve a speed up of our simulation of over 7 per, from 7 to 10 per, almost an order of magnitude, meaning that our simulations that would last 10 to 20 days can be done in 1 or 2 days, increasing the turnaround time of our simulations and improving the effectiveness of our workflow. What are examples, other examples where we can apply the GPU chemistry? This is the example of dual swirl burners that are hydrogen burners that are currently under study for future aeronautical applications. So how is this hydrogen burner is employed at the Institut de Mécanique du Fluids in Toulouse? Basically, the burner is made as shown here. We have a swirled amount of hydrogen that is injected through a gaseous injector at the center, while we have, sorry, not swirl, we have a hydrogen jet that is injected at the center here, and we have a swirled airflow that is coaxial, and it's exiting here in these two in the coaxial part. So you can see it better here. At the center, we have a jet of hydrogen. Here on the sides, we have the swirled flow of air that is mixing up with the jet here to produce an hydrogen flame. So what are the conditions here? Well, basically, we have hydrogen that is injected. It burns at a certain temperature. We have to account for an LES combustion model. We have to study by LES the mixing between the air and the hydrogen. We need to account for the multi-component transport of the different species as the hydrogen and the air mix up together. We have a mesh that is very large. Usually it ranges from 30 to 50 million cells. And we have to simulate a pretty large long time because the mixing is strongly unsteady, and we have to do LES simulation of the mixing process between the hydrogen and the air. So if we compare this problem to the typical external aerodynamic problem, we have very different conditions because the mesh apparently is smaller. When I talked about simulation of racing cars, we had 300 or 400 million cells. Here we have 30 or 40 million cells, but each time step here is much more computationally intensive because we are solving the flow transport, the chemistry, and the turbulence. If we can demand the simulation of the finite rate chemistry, so for each computational cell, we are solving the chemistry mechanism of the hydrogen. If we can demand the solution of the mechanism to the GPUs, we actually have a simulation whose weight is the same weight of a flow transport simulation approximately. We have to integrate clearly an efficient combustion model that can run either on GPUs. And if we combine all of this, we can see that we have very good matching between the simulations and the experiments for all the operating conditions of this hydrogen. When we see here anchored and lift flame, we are referred to two different mass flow rates that during combustion produce a flame that is called anchored because it is the flame is basically starts from right from the exit of the injector, rather than here the images are inverted. No, they're not inverted. Sorry. And while the lifted flame is a flame that is starting a little bit far from the injector. So as you can see here, we have a comparison between the PAV and the LES of the hydrogen injector, of the distribution of the velocity of the hydrogen at different planes out of the injector, and the matching between the simulation and the experiments is very good. Clearly, running such kind of simulations without HPC is pretty impossible because of the duration and the number of cores that are required. The HPC simulation, the number of cells, as I was mentioning, ranges from 30 to 50 million here, but the duration of the simulation onto 256 CPUs is about over a month when the combustion is turned on. Without the combustion, is clearly less than a week. If I keep looking at the combustion simulation, you can see that here on the left, you have the evolution of the hydrogen flame, and here experiment. And here on the left, you have the CFD prediction of the evolution of the OH radical, meaning that we are catching up very well the position of the flame over our domain. So the same happens for different conditions of the flame. This is the so-called lifted flame configuration. Then, if we go back to the simulation of our multiphysics problem, we have now seen that we can significantly accelerate the multiphysics problem by the ODE. But the second question is, what about the flow transport? Because as long as we have reactive flow problems and multiphysics with ODE, we saw that if we can accelerate the ordinary differential equation part, we really accelerate the calculation of the source terms, and we clearly improve our performance. But if we are not able to accelerate the flow transport, most of the non-reactive flow problems, like external aerodynamics, will not be accelerated. So the second kind of work that we want to do is let's try to simulate, to accelerate the external aerodynamic simulation. How do we do it for that? Basically, the idea is that as long as we have a CFD solver, I will start going from here. As long as we have a CFD solver, we actually have a linear algebra problem, because by the linearization of our partial differential equations, we are able to build up a sparse matrix that we need to solve by an iterative solver. So we know that GPUs have significant have a very good capability to handle very computational and intensive problems. So what we need to do is, and on the other hand, sorry, they have two bottlenecks. The first one is that they have a limitation most of the time in terms of memory, meaning that the GPU has a much more limited memory if we compare to the CPU. The second aspect is that the data transfer between the CPU and the GPU is very, very slow. This does not hold from very modern GPUs, I mean the last year GPUs, but they are very, very expensive. But for most of the GPUs most of you will work with, and also me are working with, there is a significant bottleneck in data transfer. So what we want to do to accelerate the flow transport is, let's build a matrix onto the CPU. Let's port it onto the GPU, let's solve it, and let's come back with our solution. The less time we do this, the most acceleration we get. So we need two kind of improvements on the CFD solver side. The first thing is, compared to the typical kind of solvers that we have in OpenFOAM that are segregated solvers, we need to write a couple solver, because we want to couple mass, momentum, and energy into one single matrix. This matrix, this algebra problem, is sent to the GPUs that is going to solve it. If we are doing this, we are able to actually solve these kind of problems, so the external aerodynamic of like a car or an airplane, so the typical incompressible flow, and the transonic flow around airplane, so this is the NASA Common Research Model high lift condition, we are able to solve it with a acceleration that is over 10 pairs, meaning that instead of taking 30 days on 1000 CPUs, you can take basically less than a couple of days onto a GPU. I mean, the speed up is really significant. These simulations were running onto the metrics of these simulations is here, sorry. For the segregated solver, here apparently we get only a 2-pair acceleration, but be careful because by the CPU segregated solver, we were not able to run that mesh because the solver was not robust enough. So among the two advantages of the GPUs, we have either the acceleration, but also the fact that there is a couple solver that is much more robust. When we go to the transonic solution of the transonic flow, we actually get a speed up that is from 5 to 10 pair. That depends, and I will talk about the difference between 5 and 10 very shortly. That allows us to simulate our external aerodynamics much more faster. There is, as I was mentioning, a significant issue when we talk about GPUs, which is the memory usage. The speed up that you can see here, that is 5 pair, and is different from the 10 pair I was talking about, is mostly driven by the amount of RAM memory that is available onto the GPU. So as long as you have a GPU with a limited RAM memory, you either split your problem onto multiple GPUs to share the memory, or you are limited into a certain speed up. In order to overcome this limit, we are actually simplifying very strong the communication between OpenFOAM and the AMGX linear algebra solver in order to reduce the necessary memory occupancy and in order to make the process less memory demanding and to accelerate it significantly. So this is the work we are doing today. So what's next? I mean, what is the goal? The goal is that we want to accelerate both the flow transport and the local flow physics onto the GPUs. And this is what we are doing for the simulation of hypersonic flows. What is an hypersonic flow? I will start from the image so you can understand. This is an aerospike missile. So we have like basically an external aerodynamic problem but this aerodynamic problem includes the air that is a kind of reactive. What does it mean? That when we run at Mach 10 or up from Mach 10 to Mach 30, actually from Mach 5 to Mach 30, the air becomes reactive. So you have the formation of a shock, but the temperature of this shock is so high that the air becomes reactive and it dissociates. So we need to simulate a kind of combustion problem where we have the air that is modeled by finite rate chemistry made of 22 reactions and 11 species. In order to do this, we need to, for a hypersonic flow simulation, we need to accelerate the flow transport. We need to compute the chemistry onto the GPUs, and we need to include non-equilibrium and thermodynamics and chemistry that is typical of hypersonic flows. So as you can see here, we have examples of simulations onto the GPUs of OpenFOAM under hypersonic conditions with the validations against the experimental data that are available in the literature. This work has been published by us together with Leonardo Aerospace at this SciTech conference in Orlando. Another example, as you can see, if you model properly the external aerodynamics and the chemistry, you can actually catch the proper flow physics and the proper aerodynamics of the aerospike blunt missile. What kind of simulations are these? These are unsteady simulations, reactive, So if you run them on CPUs, you are required to have about 400 to 500 cores to run for several weeks. If you run these simulations on GPUs, you can have a turnaround time of 2 to 3 days, meaning that your design workflow will be definitely much more effective. Another example of where you can apply such kind of simulations is the Orion capsule. You should have seen it at Cape Canaveral if you had the chance to go there. This is the capsule for the re-entry of the astronauts to the Earth. And the kind of simulation background that you have for such kind of simulations is the same. I mean, you have this capsule that is running at Mach 10 to 30, different operating condition. You have a bow shock in front of it. You have very high temperature here that generates the dissociation of the air. And so you have the strong radiation transfer from the shock to the surface of the capsule that may potentially cause a lot of structural problems. So clearly, this simulation that is considered very small runs in 36 hours on 96 cores. Consider that 36 hours is done on a couple solver, which is much faster than the solver that you have in the vanilla code of OpenFOAM. If you are running on the GPU, you have a simulation that is running in 4.5 hours, meaning that the number of simulations that you can run per day is definitely much higher. Here you have, we have the validation of the pressure gauge around the Orion capsule and the wall it transfer. And I would like to thank you for your attention. I'm sorry if I was too long. Thank you.
Thank you very much, Professor, for your presentation. We can now have some questions. Meanwhile, I will share a link in the chat about the evaluation of the seminar. This is a very brief evaluation of all the sessions. It will take less than a minute. It is just 5 questions. If I may say something, I found very interesting the slide about the breakdown of the users. How many threads is user utilize for OpenFOAM? And if I remember well, it was 25%. Yet the previous, I think it is the previous slide. It was 25%, less than 9 threads, more than 9 threads, 34%, etc. So it is. I understand that it is very important to yes, this one. 34%, 9 to 32 processors, etc. So the majority of users, of OpenFOAM users, need the HPC, if I understand correctly. I think we cannot hear, at least me, Professor Piscaglia, for some reason. Professor Piscaglia, can you hear us? We cannot hear you. Oh, it's only me.
Can you hear me?
Yes, now we hear, yes.
What I'm saying is this kind of survey is done on all the CFD users, not only OpenFOAM users.
CFD in general, yes.
In general, not this was done by NVIDIA. What I'm saying is usually OpenFOAM users are the ones that are using more processor cores since it is free, so it does not require additional licenses. But usually this is even in my experience, most on the industrial users usually are locked between 9 to 256 because they run several simulations at a time. They don't run one big simulation, but they run multiple. So usually if each simulation takes 256 processors, when they have run 10, they have locked the cluster. So that is what many users do.
Okay.
The
And
meaning,
if I may ask something more, do you know if you have an estimate or I mean, in which system they usually run the CFD simulations?
traditionally AMD 64 is the most wanted architecture because most of the software is running very smoothly and very easily there. You don't need specific procedures in terms of compiling and so on. While when you go to more specific architectures like ARM, or when you go to specific architectures like GPUs, the installation is a bit more complex. So installation and also usage and also extension of the code is a little bit more complex because the compilers require are a little bit more specific, in particular for GPUs. And so by now, this is the way it works, but clearly this trend is going to change very soon because GPUs are penetrating into the market very largely. So
yes,
what I'm saying might be wrong in months, probably.
Yes. Does it scale on CPU? I mean, if you have 64 processors and then you try the same code on 128, you will you will need half the time to do the simulation, or the scale is not so linear.
The scaling strongly depends from case to case. I go back to the slide just to give you the example, a practical example. I had the graph, and unfortunately, to answer very properly to your question, unfortunately, I didn't put in my presentation. Let's make a typical example, a comparison between an external aerodynamic case. So let's make a comparison between this case, where you have air around the body, okay? And the case like the hydrogen combustor, like that I showed before, okay? So this one. This is 30 million cell, let's say. The other one is 200 million cell, okay? The one that scales better is the hydrogen combustor because the single time step of each the solution of this problem is very computationally intensive because you have combustion, you have chemistry, you have turbulence. So if you parallelize it across a wider range of processor cores, that will work. So you can run easily this problem on 512 processors, even if it is 30 million cells. The other case that is 250 million, it is larger in terms of number of elements, but the computational intensity of each time step is much less than this of the hydrogen. Meaning that the scalability, if you look at the scalability range, the linear scalability of the two problems are completely different. So this is to say that a priori, the scalability is strongly determined by the physics that you are going to solve. So if I understood properly your question, you need to test case by case where your scalability, how your scalability works. The second aspect that I would recommend is OpenFOAM scales pretty well as a code. But again, that depends on the kind of physics that you're trying to solve and on the decomposition method. Because when you split your simulations over a very large number of cores, the way you decompose your mesh determines how the number of interactions that will happen between the different processor cores. Meaning that you will get pretty different scaling if you are not smart enough to decompose your domain.
Yes. Of course, I was asking because standard solvers for BLAS, usually they do not scale after 16 threads. You get the same performance, but I understand that in OpenFOAM
because if I understood your question, let's talk about physical cores and not threads. If I understood correctly,
yes.
interpret correctly, because you cannot use threads when you have CFD simulations. What I mean is, please correct me if I understood, because this might be tricky, the English part. When you have the single processor core of the simulation takes the 100% of the resources, right?
Mm-hmm.
So if you think in terms of threads, basically if you give two tasks to the same thread, each task takes the 100%.
Yes.
And then we get very bad scaling. So in terms of scalability across cores, I mean, usually if we compare OpenFOAM to the other codes, I don't see. The second aspect is OpenFOAM. I mean, most of the solvers of OpenFOAM are implicit, meaning that you don't, they don't scale as good as explicit methods do. But on the other hand, they are faster because thanks to the implicit method, you reduce the number of time steps that you need to solve to reach the final solution. I don't know if that is clear, because if I look at the combustion simulation, the one that I have here, if I use an explicit solver, I can use even 2000 cores because all the cores are almost independent and they proceed not in full independently, but pretty much independently. So the linear scalability is fantastic if I use an explicit solver of such a problem.
Yes.
But the explicit solver is forced in the time step evolution because you cannot have very large time step of integrations of your solution. So you have to subcycle a lot of time. So if you want to simulate 1 second, you do millions of time steps to reach the 1 second of final time. So even if you look at the scalability, it's very scalable, but still it's very slow because you have to do a lot of time steps. If you use implicit solvers, you will not scale up to 1000 cores for sure, but you are faster because you do less time steps. So at the end, as long as we are talking about CPUs, this works because the CPU is computationally very much performing, because the CPU is fast compared to the GPU. Single core of the CPU is faster than the single core of the GPU. But if we are talking about GPUs, clearly the explicit solvers are winning because we have a huge amount of cores available.
Yes, understood. Yes. And one final question from me, if I may.
Sure.
I have seen in other fields of finite elements that now they use AI algorithms,
Sure.
not as a solver, but as a preconditioner to obtain an approximate solution, and then to feed the solver with this solution, and then the solver will converge faster. Are there any works on CFD on that?
That is, I mean, that is a very, good question, because on one hand, the concept works very well because it's clearly you're right. I mean, if you ever use a precondition as a precondition or a solution coming from the AI, you accelerate for sure. On the other hand, if you look at the number of different cases, different conditions that I was showing only in this presentation, were good luck to train the AI model to provide you a precondition and a solution for preconditioning for each of these cases. I mean, that would take longer than running the simulation in my perspective. So as long as you have, okay, maybe in the future there will be different ways to train the AI. So if for sure there would be a big evolution, and my words will be wrong probably in a couple of months. But so far, the time required and the time and the effort required for training for such complex cases is too large compared to the amount of time that you actually need to do to do the simulation. Because if you can accelerate the simulation and to reach a turnaround time of 1 day, I don't see the point to spend months to train the model.
Yes.
But again, this might be wrong in a couple of, I mean, we don't know how it will evolve, right? Because the training,
of course, things
there is a large, steep learning curve on the AI. So
yes,
this definitely might be wrong in a couple of years.
yes,
What I'm saying.
things change rapidly. Yes. And in any case, whichever method one would try, most probably they will need the computational power. And because we are at EuroCC project, I would like to highlight that we are here to help in the process of taking access and running.
Absolutely. I think that there will be a bigger and bigger demand of computational power in the upcoming years.
Yes.
Because this is demonstrated clearly by the history. What I was meaning is, if you look at the history of CFD, well, it's true that okay, if we had to run the same simulation of 20 years ago, one core and few minutes would be enough. So the simulations that ran in the 80s on supercomputers now might run on our cell phone. But the point is that the more computer power is available, the more the CFD tries to solve challenging problems and tries to improve the accuracy of the solutions. So basically, the guys from CFD always take all the power that is available from HPC. So it never happened that they said, we are happy with this and we will not use HPC. This is never happened in the whole story. So it will not happen today or in the next years, I'm sure.
Yes,
so
definitely.
HPC will be central for the next future as much as it was in the past. I have no doubt on that.
Yes, absolutely. Okay, thank you very much,
Thank you very
Professor
much.
Piscaglia, for being in our seminar.